Attempt number 8. So in this project, I'm going to prove how to find a formula to calculate cosine's exact value at any angle theta without having to use another trig function. So first, a coordinate system. And on this coordinate system, let's have a unit circle with the equation x squared plus y squared is equal to 1. And let's say we have a triangle in this unit circle. And let's say that it intersects the circle at a point cosine of some angle here, theta, comma, sine theta. And let's define x to be cosine theta. So x will be this horizontal base here, and y to be sine theta. So that will be the height of the triangle. So first thing we want to do is we want to derive an equation for the area of all of this bounded area here between the circle and the triangle, and this angle theta here in radians, and you'll see why in a moment. So how we do this is, let's take some infinitesimally small cross section of the circle here. So here the circle is pretty much horizontal. Now let's say that the radius increases by an infinitesimally small dr. So our arc length here is L, and we know that the area of this bounded area changes by an amount dA. So that's an infinitesimally small change in the area, so we can write that as a differential. So dA is equal to, and since this is approximately a rectangle, we can say L dr. And now we can integrate. So A is equal to, we can't integrate this yet because L changes as R changes by an infinitesimal amount, and that amount, by the definition of a radian, L equals theta R, that amount is going to be equal to theta times R. So now we can integrate. Theta does not change as R changes since our arc is still the same. So then we get that this becomes theta R squared over 2. And there would technically be a plus C there, but if R is 0, then A is obviously 0, so C is also going to be 0. And this describes the area under this arc and the triangle here, because this describes the border of this arc here, this bounded area. So now we know that R is going to be equal to 1 since we have a unit circle. So this area is just theta over 2. And that's going to describe this area in particular because of this equation right here. And since this is just nothing but the edge of this bounded area, so now we get that theta over 2 is equal to, and then we can find this area in terms of x and y. So that's base times height divided by 2, xy over 2 plus the integral of this area here, which is integral from x to 1, since x is our left bound and 1 is our right bound, of y dx. And we know from this equation that y is equal to square root 1 minus x squared. So then now we get that theta, multiplying both sides by 2 and plugging in for y, is x square root 1 minus x squared plus integral from x to 1 of, that's 2 times the integral, 1 minus x squared dx. And that's about as far as we can go with the integration, because a lot of this is beyond the calculus AB, since we can't integrate this the way we normally would in AB. Usually we would do pi r squared, but this is only a fraction of a circle, so we can't do that. Neither can we use BC techniques, because BC would usually use trig substitution, but as we said earlier, we don't want to find cosine in terms of another trig function. So we're going to avoid that, but what the integral ultimately comes out to is a function f of theta, where f of theta is equal to the natural log of square root theta plus square root 1 plus theta divided by square root theta minus natural log of x square root theta plus square root 1 plus theta x squared divided by square root theta plus c, where we know that f of 0 is equal to 1 minus x, and f of -1 is equal to our original value of theta. Now, something important to note here is that theta is not related to x. So if we plug in a value for f of theta, x will not change, it will still be x. So if we plug in 0 here, we get natural log of 0 plus square root 1 plus 0, which is just 1. So ln 1 is 0 divided by square root 0, that becomes indeterminate. Same thing here, natural log of 0 plus 1 is just 0 divided by 0, and that's indeterminate. However, we can use L'Hopital's rule to simplify this, since they are both indeterminate. So we know f of 0 is 1 minus x, which is equal to the limit as theta and theta only approaches 0 of, and then we take the derivative of the top and bottom for each one. So we get 1 over the argument of natural log. And then we use chain rule for the inside. And then we can't forget about this square root theta on the bottom, so we divide by its derivative. Its derivative is 1 over 2 square root theta. Dividing by that, we get times 2 square root theta. And before we move on to this next term, we can simplify this by multiplying the numerator by 2 square root theta. So what we get when we do that is 1 plus square root theta over square root 1 plus theta. And then now we can move on to the next term, minus, once again, the argument goes on the bottom. And then on the top, we use chain rule for the inside. And here, x is a constant, so this goes on top. And now we have that, but we once again add this, or multiply by 2 square root theta to account for this, and using L'Hopital's rule. And now we can simplify this. So this becomes x plus x squared square root theta divided by square root of 1 plus theta x squared. All of this plus c. So now what happens when we plug in 0? We get 1 plus 0 over square root 1 plus 0, which is just 0, so we just get 1 on the numerator, divided by square root 0 plus square root 1 plus 0, that's also 1. So this whole left term becomes 1. And then this next term becomes x plus x squared square root 0 divided by square root 1 plus 0. So all of that just becomes 0. And then the numerator, like before, just becomes 1 because we have 0 times x plus square root 1 plus 0, which is all just 1. So this becomes minus x. And then plus c. So after all of that, we can see here by comparing these two that c is going to be 0, which might have made this whole thing seem useless, but remember, if c was not 0, then our whole calculation would be thrown off. So this was a necessary step to make sure that our calculation was correct. So now we can erase all of this. And now we can erase plus c. And then remember, f of -1 was equal to theta, as we said earlier. Theta equals f of -1, which is equal to natural log of, plugging -1 here, we get square root -1 plus square root 1 minus 1, which is all just ln I, which is square root of -1, divided by I, once again, minus natural log of xi plus square root 1 minus x squared, all of that divided once again by I. So this at first looks terrifying because we have natural log of an imaginary number, but we can easily get rid of that. And how will we do that? Well, let's factor out an I here. So to do that, we simplify this into square root negative x squared minus 1 in parentheses. And now we can factor out a square root -1 out of this square root, and then we get that this is just I square root of x squared minus 1. This is an I, by the way, not a 1. So now we can factor out of all of this, since we have an xi at the beginning, we can factor out an I. So now we have natural log of I times x plus square root x squared minus 1. And remember, if you have, oh hold on, there needs to be parentheses in here. Remember, if you have a natural log of two numbers multiplied together, let's say natural log of a times b, that's the same as saying ln a plus ln b. So then this becomes ln I over I minus ln I plus ln x plus square root x squared minus 1, all divided by I. And then the ln I over i's cancel out, and we get negative ln x plus square root x squared minus 1 over I, and that's of course equal to theta. Now that we have all of this done, we can solve for x, which remember is cosine theta. Right now, this is arc cosine theta, because this is just arc cosine of cosine theta, which is just theta. So now if we try to solve for x, we get that natural log of x plus square root x squared minus 1 is equal to negative I theta. So then x plus square root x squared minus 1 is equal to e to the negative I theta. Now, what we can do to simplify this is we can use a quadratic equation. So remember, if you have an equation ax squared plus bx plus c equals 0, then x is equal to negative b plus or minus square root b squared minus 4ac, all of that divided by 2a. So now we want this equation to look more like this. How do we do that? Well, let's say that we multiply the top and bottom by 2. So this becomes 2x plus 2 square root x squared minus 1 divided by 2 equals e to the negative I theta. And to simplify this further, we can move the 2 to the inside of the square root because 2 is just square root of 4. So then this becomes square root of 4x squared minus 4. So we can see by doing that a is going to be 1, c is going to be 1, and this term is analogous to this term, so negative b is equal to 2x. So b must be negative 2x. And we can see that in here as well, because 4x squared is the same thing as saying negative 2x whole squared. So now we have that e to the negative I theta is our x, b is negative 2x, a is 1, and c is 1. So now if we reverse this quadratic equation, we find that e to the negative I theta squared plus, that would be minus, since b is negative, minus 2x e to the negative I theta plus 1 is equal to 0. Now we isolate x. So e to the negative I theta squared plus 1 equals 2x e to the negative I theta. And now to solve for x, we just divide both sides by 2e to the negative I theta. So then we get that x, or cosine theta, is equal to e to the negative I theta plus e to the I theta divided by 2. And this is our semifinal solution. So, you can notice that this works because if you plug in 0, then you find that e to the 0 plus e to the 0 over 2 is just 1 plus 1 over 2, which is 1, and that's cosine 0. And if you plug in, let's say, pi, remember from Euler's famous theorem, or Euler as it's correctly pronounced, e to the pi I is equal to negative 1. So if we plug in pi here, we know cosine of pi is the negative 1. So we have e to the pi I, or negative 1, plus e to the negative pi I, which is just 1 over e to the pi I, which is also negative 1. So negative 1 minus 1 over 2, that's going to be equal to negative 1. And if we plug in 2 pi, then we can see here that e to the pi I squared is equal to negative 1 squared. So e to the 2 pi I is equal to 1. So when we plug in 2 pi here, e to the 2 pi I is 1, e to the negative 2 pi I is also 1. 1 plus 1 over 2, that's going to be equal to 1, which is the real value of cosine of 2 pi. However, you'll quickly notice that for values such as pi over 4, then you would have to bring this to the power of 1 over 4, 1 over 4. Then we get that e to the pi I over 4, pi I over 4 is equal to square root of I. But square root of I doesn't have a known value. So we're going to need to come up with a more useful form of this equation. And to do that, let's start by finding sine. So remember, sine theta is just the integral of cosine theta d theta, and that's equal to the integral of e to the negative I theta plus e to the I theta over 2 d theta. And that's just using u substitution. That will become, I believe, e to the I theta minus e to the negative I theta over 2I. And that's the same thing as saying negative I e to the I theta minus e to the negative I theta divided by 2, because 1 over I is just negative I. Since if you multiply the top and bottom by I, then you get I over I squared, which is just negative I. So now what we can do is we can work with cis of theta, which is cosine plus I sine. So then that becomes e to the I theta plus e to the negative I theta over 2 minus, or no, yeah, that'll just be plus, since negative I times I is negative I squared, or just 1, plus e to the I theta minus e to the negative I theta over 2. So what we can do is we can combine all of these terms since they have a common denominator. So it becomes this, and the e to the negative I thetas cancel out, and we get 2e to the I theta over 2, which is just e to the I theta. So we get that cis of theta is equal to e to the I theta. And this is already really useful because we can prove the Mavoir's theorem with this, which, if you remember, is basically just r cis theta to the n equals r to the n cis n theta. But right now, we're just going to use this to prove a more useful formula for cosine. So now what we can do with this is we can use Euler's theorem from up here, and we can convert it to a more useful form. So remember e to the pi I equals -1. So if we raise both sides to the power of x over, or no, let's not use x, that's confusing, theta over pi, so this also to the power of theta over pi, we get that e to the I theta is equal to -1 to the power of theta over pi. So now what we can do is we can equate this to -1 to the theta over pi. And now we can solve for -1. So let's replace cosine and sine with x and y like we did before. So x plus y I. We raise both sides to the pi over theta so that -1 is isolated. So to the pi over theta is equal to -1. So then now we find that plugging in for y, we find that x plus I square root 1 minus x squared to the power of pi over theta is equal to -1. And this is our final equation, a lot more useful than our first equation because now we can calculate it for any value of theta. Even if it's not a multiple of pi, we can still calculate it because we can use a binomial expansion, which is just a way of finding out the expansion of all of this for an infinite, or for a non-integer power. So if this was, let's say, pi over 3, then we could use a binomial series to expand this into an infinite series and set that equal to -1. And we will know that the imaginary part will be equal to 0 and the real part will be equal to -1, since -1 is the only real term on this side and there is no imaginary term. And so using that equation, we can use some simple calculations to find any value of cosine and its exact number. And the reason that this is useful is, first of all, because this allows to calculate any exact value of cosine at any angle, even at pi over 4, which, if you remember, we were not able to do a minute ago. And second of all, the process that we use to get this equation is it's found the basis of all or almost all imaginary calculations, because this allows you to, this definition of cosine allows you to interchange between real numbers and imaginary numbers using any power. So like if you had like 2 to the I, you could solve that using this definition, although that's really something that will get a little more complicated. But it's still a valid application, and there are many more applications in imaginary numbers that stem from the whole process that we use to get this final solution. You can also rearrange this to solve for other functions like sine or tangent at their exact values. However, for now, this is as far as we will go in our project. So this is finding an exact value for cosine using calculus and some simple math besides that. And that's my project.